Alright, grade 12, so we're now going to do the next little section. So this is part 3 of our acids and bases, and now we're going to look at how pH is related to the relative strengths of acids and bases and how we can sort of combine the two together in terms of the acid-base equilibrium. So now what you need to remember is we can compare the acids and bases strength by looking at the equilibrium constant. This is the same equilibrium constant that we used for equilibrium. Alright, so obviously the size of the equilibrium constant tells me a lot about how much product we've got. And this is quite important. So when we look at an acid, the acid ionization constant is actually fairly straightforward. So what we have here is, and this is just an example, we have the acid, which we're going to put into water, and we get H3O plus and Cl minus. Right? This was an equilibrium question. We would have gone fine. Let's put the equilibrium constant, remembering we don't put the H2O in because it is a pure liquid, which then means that my equilibrium constant is the products, H3O plus times the Cl minus divided by the reactants, just like before. But now what I want you to see is this has become a Ka, because it's the equilibrium constant for an acid. So it's very specific, okay? Obviously, the size of this value is going to determine whether we have a strong acid or a weak acid, remembering what our definitions are. So remember, first of all, the Ka, this is not remember, this is new. The Ka is called the ionization constant for an acid. It's the equilibrium constant. A strong acid ionizes completely, or close to completely. We will assume it's complete ionization because it's easier for our calculations, okay? In higher, right, so strong acids will have a high Ka value. In other words, the Ka value will be greater than 1 because it means we have more product than reactant. Strong acids have a low Ka value, which means the value is going to be less than 1 because we have more reactants, and that's at the bottom. When we look at a base ionization constant, now this is dissociation or ionization with a base, because remember, bases generally dissociate because they're ionic. So if we consider the following base, here we have ammonia reacting with the water, which creates our ions. What we're really concerned about is whether we have a lot of these ions at the end. So we would normally set up our Kc value with the products over the reactants. We don't need the water because the water is a pure liquid, so we don't put it in. And then that gives us NH4 plus and OH minus over NH3. Once again, now we're changing a little bit. We've got now a Kb instead of a Kc because we're looking at the equilibrium constant with regards to the base as it dissociates or ionizes in water. Okay, now this time it's called the dissociation constant. Dissociation because most bases dissociate. A strong base dissociates almost completely. We've spoken about that. So there's more product, so it's a high Kb value. Strong bases have a high Kb value. That means we have a value greater than 1. Weak bases have a low Kb value, which means they have a value less than 1. All right, now I need you to make a note here in terms of your book. Your book now goes through calculating the pH of strong acids and bases, and they use a whole bunch of stuff with equilibrium and all sorts of things. Please, this is not examinable. It is completely and utterly extension. Same with the calculation of the pH of weak acids and weak bases. That should be okay. There's no K there. All right. Please, this is very important. Don't spend time on it. We will only work with acids and bases where we have 100% ionization for the pH calculation. Okay. When we compare the strength of an acid or a base, if we don't know the pH, we can actually compare by looking at other things, all right? One of them is conductivity, and by conductivity, we're talking about electrical conductivity. Strong acids and bases are very good conductors because there's lots of ions in the solution. Weak acids and bases aren't good conductors because there's not a lot of ions, so they don't conduct electricity well. When we look at the reaction rate, strong acids and bases will react faster than weak acids and bases of the same concentration because even though the concentration is the same because we put the same number of moles of the acid or the base in, with a strong acid we have a lot more ions. If we have a lot more ions, the reaction will happen faster. Okay, so now if we look at a quick example, they say here, which sample in each of the following pairs will conduct electricity the easiest? What they're actually asking for here is which one is the stronger acid or the base. So here we have HCl and H2CO3, carbonic acid. When we look at it, well, it's going to be HCl. It is a stronger acid. Now we have calcium hydroxide and sodium hydroxide. For this one, sodium hydroxide, absolutely, because it is a much, 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 much stronger base. Okay, it's a very strong base. Which sample in each of the following pairs will react most vigorously, in other words, faster? Once again, I'm asking you which one is stronger, potassium hydroxide or magnesium hydroxide. Well, it's going to be the potassium hydroxide because it's a group 1 metal base. And then we've got acetic acid, otherwise known as vinegar, with sulfuric acid. And you should hopefully know that vinegar is a much weaker acid than sulfuric acid. Okay? Nice and easy section. Now we're going to go to unit 17, which is hydrolysis. This one's really, really important. Okay, so I need you to stay with me here. When an acid and a base react with each other, they form a salt. That salt doesn't need to necessarily be neutral. So we have this idea in our heads that when an acid and a base react, they always give us a neutral solution. That is not true. It all depends on the strength of the acid and the base. So a neutral salt can only be formed. So our final solution is neutral only if we have a strong acid and a strong base. Because what happens is a salt that's formed, that salt can then react with the water. So if they're not of comparable strengths, the salt that's formed can react with the water, and that reaction is called hydrolysis. And with hydrolysis, it's really important because knowing whether the salt that's formed will react with water is quite important when we choose an indicator for a reaction. Okay, so let's look. So here we have a salt, sodium chloride. Now, sodium chloride was made from a chemical reaction. That chemical reaction would have been made from an acid and a base. So I have to decide which acid and base came from. The metal always comes from the base. Make your life easier, we'll say it always comes from a hydroxide. So the Na ions were put into the solution by sodium hydroxide. The chloride comes from hydrochloric acid, also a strong acid. Now when this salt now reacts with water, so now we put it in water, it's going to dissolve. It then splits up into its Na plus ions and the Cl minus ions. These will not react with water. So there's no hydrolysis, and my final solution is neutral. The reason why these don't react is because they came from strong acids and a strong base. Okay, the Cl minus is the strong acid's conjugate base, but it's the exact opposite of a strong acid, so it's a weak conjugate base. The strong base forms, the Na plus essentially forms a weak conjugate acid. Okay, don't worry about the fact that it doesn't have a hydrogen for now, that doesn't matter. But the point is, as soon as I form weak conjugates, those ions won't react because the strong acid and base desperately want to react. Once they reacted, they're like, we're happy, we don't need to react anymore. So nothing will happen. If now we look at something like ammonium chloride, now there's no metal to break this up, but you do need to recognize that the ammonium is going to come from ammonia, which is a weak base. Okay, which means the NH4 plus ion, which is created, has actually become a strong conjugate acid. It desperately wants to get rid of that extra hydrogen now. The Cl comes from hydrochloric acid. Same as here, it's become a weak conjugate base. It's like, yeah, I don't want a hydrogen back, we're fine. So when this gets added to water, and that water forces it to break up into NH4 plus and Cl minus, the Cl minus isn't going to react because it's a weak conjugate base. The NH4 plus is absolutely going to react because now it's a strong conjugate acid. It desperately wants to get rid of this. So the NH4 plus will react with the water, and as a result of reacting with the water, creates lots of H3O plus ions. Those H3O plus ions make it acidic, so my final solution is acidic. Weak base, strong acid, gives me acidic salt. Okay, so we would say that that is an, whoopsie, let's write this so you can read it. This is an acidic salt. This is a neutral salt. Okay, so now we look at K to S. Split it up. It's going to come from potassium hydroxide, absolutely a strong base, which means the potassium, essentially that potassium ion, is a weak conjugate acid. It's like, yeah, I don't really feel like reacting. The S is going to come from H2S. H2S is a weak acid, which means the S2 minus has become a strong conjugate base. It desperately wants to react. It doesn't want to stay as S2 minus. All right. As a result, when I add water to this and it breaks up, the S2 minus ions will react. They will then give me OH minus ions. Those OH minus ions make the solution basic. Okay, this would be known as a basic salt. Okay, so what you need to get here, because this is actually quite important. Even if you're not 100% sure of what happened with the hydrolysis part, this is the important part, okay? The salt of a strong acid and a strong base is neutral. Strong acid, weak base is acidic. So in other words, the salt takes on the nature of whatever's the strongest. Weak acid, strong base, it's a basic value. This is why it's important that you know strong acids and weak acids. Okay? Very, very important. So, let's look at an example. What will the resulting pH be when potassium chloride is dissolved in water? And explain with the use of equations. So here we go. KCl is produced from HCl and KOH. How do I know? Because I break it in half. Strong acid, strong base. That means K plus and Cl minus ions will not react with the water. The solution is pH 7. It's neutral because it came from a strong acid and a strong base. If I look at calcium nitrate, well, when that, okay, there we go. Sorry, let's give you some time. Calcium nitrate, remember, you're going to break it up. So your base is going to be calcium hydroxide, and your acid is going to be H2NO3, nitric acid. Calcium hydroxide is a weak base. Nitric acid is a strong acid. Okay, so now watch. Calcium hydroxide is produced from a weak base and a strong acid. There's the reaction. The calcium plus ions will react with the water. I will never ask you to work out how that reaction happens. Okay, that's just never going to be one of the things you need to do. Therefore, the solution will be acidic and the pH will be less than 7. At this junction, I really need you to do activity 1 on page 272 before you move on to the volumetric analysis.